Alright, welcome my Z-stars. This video is on connecting sampling distributions to confidence intervals, but this video specializes on explaining it for means. There was another video for proportions, this one's more about means. So let's first make sure you understand a really important thing. What the heck is a population parameter? A population parameter is the true value that we know for a population. For example, the true proportion of people that smoke cigarettes. Now that is versus a sample statistic, which is information that comes only from a sample, and that would be p-hat. Like the sample, what proportion of people smoke in a sample of 50 people. And then we also have means, right? The true mean of an entire population is mu versus the mean of a sample is x bar. And then we also have standard deviation, which piggybacks off that. The standard deviation of a population is sigma, and the standard deviation of a sample is s. So make sure you keep those symbols straight. It's a really important part of statistics. All right, so realistically, the idea is that a sampling distribution is a lot like deductive reasoning. We start with knowing the truth. We know what the truth is. We know what the true population parameter is. We know the true mu, and we want to build a model that shows us what all possible sample statistics, like x bar, for a specific sample size would be. So we know the truth, but we want to make a picture of what all possible sample means could be. Now, it's actually pretty crazy that we could create this picture of all these different possible sample statistics without actually looking at a single sample. And this is really the power of sampling distributions and statistics. So let's take a look at an example here. Pretty fun example I came up with. So the mean height of a giraffe is 22.3 feet with a standard deviation of 2.5 feet. All right, so again, we know the mu, we know the sigma, we know the truth, right? They're telling it to us. Deductive reasoning here. Let x bar, there should be a bar above that, I'm sorry. Let x bar be the sample mean of a sample of 12 giraffes. Describe the sampling distribution. So, if I took out a sample of 12 giraffes, what could their mean look like? Well, I don't know. I guess it could be 22.3. It could be higher. It could be lower. Who knows? But a sampling distribution will allow us to understand that. So here's what we know. We know the true mean is 22.3 feet. We know the true standard deviation of the population is 2.5 feet. All right, so, what's the center of our sampling distribution? What's the mean of all those possible x bars? Now, cool thing, I haven't even looked at a single x bar, but I'm already thinking about what the mean of all of them would be. Well, guess what? It should be 22.3. Because in a sample of 12, you would go into that sample expecting to get 22.3. You might get something higher, you might get something lower, but the expected value is going to be 22.3. Again, as long as the samples were taken randomly to avoid bias. Now, there is a standard deviation as well. And most people would say, wasn't the standard deviation 2.5? Well, the 2.5 is for a single giraffe, how a single giraffe could deviate. Single giraffe could be taller, 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 shorter, shorter, shorter. But we're no longer talking about a single giraffe. We're talking about this standard deviation of a sample of 12. So remember, bigger samples do vary less. So we take the standard deviation and we divide it by the square root of our sample size. And that's how we get the standard deviation. Now keep in mind, this formula is only allowed to be used provided that our sample size is under 10% of the population. And I think it's pretty safe to say that 12 giraffes is under 10% of all giraffes. So I get a standard deviation of 0.72. All right, now I'm allowed to build my model, right? My picture of my model, which I know has a shape that is normal. Now, actually, there's a little bit of an issue here because, the third condition says I need to be big enough to make this shape. And with a sample of 12, the central limit theorem can't really help me there. So I would need to know that the heights of giraffes does follow a normal distribution to begin with. And for the most part, heights of any mammal does follow a normal distribution. So 12 should be big enough. So right smack dab in the middle of this is going to be 22.3. I can go up 1, I can go up 2, I can go up 3, I can go down 1, I can go down 2, I can go down 3. For pure sake of trying to fit these numbers in, I'm just going to round my standard deviation to 0.7. So this would be 23, 23.7, and 24.4. Going down, this would be 21.6. 20.9 and 20.2. Hopefully I did all that math right. All right, now what does this model actually show me? Well, it shows me what a bunch of X bars are going to look like. Now remember, I haven't even taken a sample mean yet, but this tells me that, most sample means are probably going to be somewhere between 20.9 and 23.7. That's what would be very common. That's where 95% of samples fall. They kind of fall in that area there. And, occasionally a very... Well, excuse me, a very weird sample would be way up here, a very weird sample would be way down here, but for the most part, samples of 12 giraffes will fall somewhere in there. All right, so now we might ask you a question like this. Hey, suppose that a sample of 12 giraffes actually came back with a mean of 19.5. So let's suppose that a mean was 19.5. Now, I'm already a little bit like scratching my head like, boy, oh boy, 19.5, that's way down here somewhere. That would be pretty weird. So, let's find the probability that a sample, I almost was going to write p hat there. This isn't proportions, this is means, man. So what's the probability that a sample mean would come back at 19.5 or lower? That's what they asked me to find here. So the first thing I need to figure out is exactly where does 19.5 fall, and I could do that with a z-score. So I'm going to take 19.5, I'm going to subtract the center, 22.3. I'm going to divide by the standard deviation of 0.72. And that's how you find a z-score. Pretty easy formula. When you do the math on your calculator, please make sure you do the top first and then divide by the bottom. Try to do it all at once. Sometimes you can mess that up. And we get negative 3.8889. And that is a very low z-score. This is telling me that, boy, oh boy, I got a surprising sample. I got a crazy low sample. Now, traditionally, I don't really believe in these crazy types of things happening, but hey, this is a really, really low sample. Now, to find the probability, I do need normal CDF, or if you were living back in prehistoric times, you could use one of the old normal Z tables. So this time I'm going to start with my Z-score of negative 3. Actually, I'll take that back. I'm going to start way down low at negative 99. Because if I'm looking below, I got to start way below negative 99. And I'm going to stop at my z-score of negative 3.8889. And this is going to find the probability that I am a value below negative 3.889. And I get, oh my goodness, this is unbelievably low. That e to the negative 5 tells me I've got to move the decimal 4 times to the left. So that's going to be 0.00005. Very, very unlikely for a sample like this to happen. Now, traditionally, if a sample like this did actually happen, like I'm telling you it did, it usually tells me something, but I don't want to dive into that right now. The point I'm trying to make is that this is a crazy, unbelievably low sample. All right, now, let's connect sampling distributions back to confidence intervals. That's the whole point of this video, right? So, creating a confidence interval for a population parameter is like inductive reasoning. Here, we don't know what the true population parameter is. I don't know what the true mean is. I have no idea. So let's pretend that we have no idea how tall the average giraffe is. So what we do is we take a single sample statistic, we take an X bar, and we're going to use that sample statistic as an estimate for the population parameter. But one value is not good enough to estimate the truth, so what we're going to do is we're going to wrap an interval around our sample statistic in hopes of capturing the truth. So suppose that we went ahead and got that sample of 12 giraffes, and that sample did come back with a standard deviation of 1.9 feet, right? So remember what we saw already. Our sample mean was 19.5 feet, and now what I'm telling you, and you'll see why I need this information, the standard deviation of my sample is 1.9 feet. Now remember, when you create a confidence interval, you're pretending that you don't have any idea what the true value is. So that's why I have to pretend that, I don't remember anything from up here, right? Up here we had the mean was 22.3 feet, the standard deviation of all giraffes was 2.5 feet. I'm pretending I don't know that. The only thing I know is my sample, and that is the 19.5 and then 1.9. So now what I'm going to do is I'm going to try to use this sample to find the truth. And I'm going to start off by taking my mean of my sample, and I'm going to go up and I'm going to go down. I'm going to wrap this interval around it, and that's called the margin of error. Now, because I don't know sigma, the only thing I know is the standard deviation of my sample, I have to use what's called a T star from the T model. You should have learned about this in class. So to get your T star, you're going to go to invert T on your calculator. Now for 95% confident, the area it's asking for is the area at the bottom. If you're 95% confident, that puts 2.5% at the bottom, which also puts 2.5% at the top. But again, the calculator only wants the bottom. The degrees of freedom would be your sample size minus 1, so 11 degrees of freedom. And this gives me 2.2009, which if you run that correctly, would be 2.010. 2.0100. Or wait a minute, did I run that correctly? I'm sorry, 2.201. I knew something sounded fishy as soon as I said that. So 2.2010. All right, now I need my standard error. And again, this is where I had to use the T model because the only standard deviation I know is the standard deviation from my sample. I don't know the standard deviation from the entire population. In the above problem, I did know the standard deviation of the entire population. That's why I used a normal model. Here, I don't know it, so that's why I have to use the T model. So that back number, the 2.2010 times 1.9 divided by the square root of 12, that back number is my margin of error. So I have 19.5 plus or minus 1.21. All right, so now I can create my interval. I could take the 19.5, I could go down 1.21, and I get a mean as low as 18.29. And then I could take the 19.5, I could go up 1.21, and I get as high as 20.71. So I'm 95% confident that the true mean height of a giraffe is somewhere between 18.29 feet and 20.71 feet. But guess what? I'm wrong. Remember, the true mean was 22.3 feet. And this is actually good, right? This is what was supposed to happen. Remember, our sample of 19.5 feet, we knew when we had the sampling distribution, was extremely, extremely low. It was extremely low, right? It was not one of those very common samples. In fact, the probability was very unlikely. So when I wrapped my interval around, so I'm kind of running into things here, but I wrapped my interval, I went down a little bit, I went up a little bit. Notice that I missed the truth. The truth was not in my interval. And that's why we tell you guys that, we're 95% confident. 95% confident means that 95% of samples are near the mean, and that a sample that is found near the mean will contain the mean in its interval. Well, that does leave us with 5% of unconfidence, I guess you could call it. You could call it. And the idea here is, I've actually talked about this before, when the truth is not in your interval, what that means is that your sample must have been very, very unlikely. And this is an example that's showing you that, right? Yes, I know most samples should have been in here somewhere. But the fact that the truth was not in my interval means that my sample had to have been one of those crazy, crazy low, unlikely samples. And guess what? It was. So the whole point I'm trying to teach you in this video is that sampling distributions are connected to confidence intervals. When you build a sampling distribution and you find a particular sample, you can analyze how high or how low it is. But a confidence interval, you have no idea what the truth is. So you build an interval in the hopes of capturing the truth. And the idea is if you get a sample really, really crazy high or crazy low, yes, you will miss the truth in your interval. But that should not happen very often because crazy samples like this one right here are very rare, very unlikely to occur. So I hope in this video you're really kind of understanding how sampling distributions is deductive reasoning, confidence intervals are inductive reasoning, but they blend together to understand the same overall idea. And I really hope you understand that concept moving forward. It really will pay a lot of dividends later on when we get into some tougher problems. All right, guys, see you on the next video. Can't wait. Please subscribe to my channel.